So hello guys, so today we are going to see today Leetcode question. You are watching Export Funda, and today we have given question is 958. This question is check completeness of the binary tree. So first we will understand the binary tree of the completeness, and then we will understand the statement. Okay, so actually a statement is saying that we have given the root of binary tree and we have to determine if it is a complete binary tree or not. Okay, in the sense we have to say true or false. Okay, either this is a complete binary tree, then we have to say true, otherwise we have to pass false, right? So let's understand the complete binary tree. What is complete binary tree? So every level except possibly the last, right, is completely filled, and all nodes in the last level are as far as the left as possible. Okay, so it can have between 1 and to the power h, that is h is the height of the last level of the you can say binary tree. Okay, so if I'll talk about the binary tree, okay, so first of all let's understand this one. Let's suppose this is the example, right? So this is we have it is called root node. Okay, this is a root node, right? So if we talk about the level, right, so the level will be 0 here for this one. Okay, for this level, this is level 2. Similarly, for this level, this is level 3. Okay, and if we'll talk about the children's, so these are for this root node, right? This root node, these are children. Okay, this is children, this is also children, right? And if we'll talk about this one, so this 4 and 5 node are children of 2, and 3 have children 6, and another is none. Okay, so if we'll talk about the parent node of 5, right? So parent node of 5 is what? 3. Okay, if I will talk about parent node of what? 5, so it is 2. If you talk about parent node of 2 and 3, it is 1, right? So I think you have understood, right? So child node is what? This is child node 1 and child node 2. Similarly, child node is 1 and there is another is null, right? But if you talk about this node 1 and the child node is 1 and child node is 2. Okay, so these are the, you can say, terminology we will use into the you can say solution. Okay, so complete binary tree is saying that if the every level, right, so there is level what? Level 1 we have, level 2 we have, level 3 we have, right? So all levels we have, right? So all level except the last one, this the last, this is our last level. Okay, so all level except the last is completely filled. So you can see level 0 is filled, level 2 is filled, only the last 3 is not filled because there is one null node is there. Okay, and all the nodes in the last are last level are as far as left as possible. So you can see first left is filled, but right is not filled, so this left should be filled. Okay, and it can have between 1 and 2, right? It can have between 1 and 2 to the h nodes inclusive last level. So if you talk about this one, so last is what? 2 to the power 3, so it should be what? If you count, it will become 2 into 2 into 2, so it will become 4 into 2 is 8, right? So if you count the node, right, it will become what? 1 2 3 4 5 6, right? 6, and this is 7, so it should be less than, it should have between 1 and 2. So you can see total how many nodes we have? We have 6 nodes, right? We have 6 nodes, so it is between 1 to 2 to the power h, and that is, this is true, right? So that's why if we'll see the input, right, inputs is given 1 to 6, and that's output is saying true because every level before the last is full, right? Because the level with the null value is what? With the node value is what? First is 1, that you can see in the level 1, then we have 2 3 level 2, and all the nodes in the last level is what? 4 5 6, and that are as fast as far left as possible, right? That is, so that's why it is we can say complete binary tree. And if we'll talk about this one, right, so this is level 1, this is level 2, this is level 3, right? But you can see this part is not filled, right? So that's why it is saying the node 7 isn't the as far as the left as possible, right? So this is null, so it should not be the null, right? And that's why it is saying that it is false. Okay. And uh, if we'll talk about the constraint, right, so number of the nodes in the tree in the range is 1 to 100, and value is 1 to 1000, right? So these two constraints we have given. Now think this question is also asked in the Facebook more than 7 times, and Apple. This question is important, you can say, and this question belongs to the topic that is tree, binary search tree, and sorry, breadth first search, BFS, and the binary tree. Okay, so what we will do, we'll try to implement through the binary first, BFS, breadth first search, and we'll do the implementation. Okay, so see, we can see the binary tree is complete, right? If there is no node to the right of the first node, and no node at the greater level than the first null, okay, null node, it means if we traverse the tree level by level, right, from left to right, and we come across null node, all the subsequent nodes in the this traversal should be null as well, should not exist, you can say. So the level order traversal array of the complete binary tree will never have a null, right? So if we'll talk about this one, right, so first if level order is 1, now we have 2, 3, now we have 4, 5, null, right, and then 7. So this null should not come. Okay, that's why it is saying that when we are going with level order traversal of a complete binary tree, will never have a null node, right? Like previously, if we'll talk about this one, it will, the traversal is what, first came 1, then it come 2, 3, then it come out 4, 5, and 6. Null is not here in between this, right? And that's why it is complete binary tree. And this is coming what you can say 1 to 7, there is a null is coming, right? And that's why it is saying that it should not have the null value. Okay, so in the breadth first search, traversal can be used to perform level wise traversal, right? And the BFS algorithm for traversing or searching a graph. Okay, so if it traverses in a level wise manner, and all the nodes at the present level, let's say 1, are explored before moving on the nodes of the next level, level 1 plus 1, okay, current level plus 1, and where a level number is the distance from the starting nodes, you can say, and BFS is implemented with the queue. We will use the queue, and then we will do, right? So what we will do, we will try to we will begin with the root node, and we will return true if the root is null, right? The first cases will do that. Okay, and if we will go to the what we can say, if it is empty, right, then we will, so it is complete binary tree. Otherwise we will initialize a boolean variable and call null node found, and to keep track of whether or not we have seen a null node, and we'll set it to false at the start. Okay, and that we will do. Okay, so first we'll start from the root. If root is what, it is a null, then we will say, we will return from here, and we'll say it is a complete binary tree. Otherwise what we'll do, we'll go to the its kids, right, and its children, and we'll say, yeah, only 2 will be there. Okay, so we'll say if not null is found, right, either we'll do what, to keep track of finding a null node will found, and if that is found, right, then we'll set to false. If not found, then we'll say it's complete binary tree. Okay, so we'll start a BFS pushing root to the BFS queue. We will put into the a queue, you can say, and while the BFS queue is not empty, we fetch the front node in the queue, and we'll check if node is like root we check, right? So we'll check node is not null, right? If it is not null, or if it is null, then we will say null node found, and we'll say true. Otherwise, if not null, then we will check we have already visited a node or not. If we previously visited a node, right, into the from the queue, right, so we will update this, right, and if already visited, then we will say node null, and the given tree isn't binary tree, and we set encounter node visiting it. In that case, you know, right? So if we haven't visited null node, then we'll say null node node not equal to null, and we'll push into the node dot left, means its left children we will put, and then similarly we'll put right children. Okay, so let's go to the, you can say, so we are here at the complete, we will check, we have given what root node we have given. So what we will do, we will add a root node null if root is not null, right? If root is not null, then we will traverse. If root is null, then we will say it is a complete binary. Okay, if not, then what we will do, we'll create one boolean check null node. Okay, we'll check a null node, and it is a by default will take a false, and if we will update each time, right? So we'll take a queue, and we'll say queue is a tree node, and this is what we have, queue, and this queue will take what new, this is nothing but a linked list, you can say, and that's all. Now what we will do, we'll add onto the queue okay, queue dot add will do, and we'll add onto the add is also there, offer is also a method, so we'll add offer, and we'll add our root. So this is done. Now what we'll do, we'll check onto the queue while if queue dot is empty method. Okay, so if it is not empty, means we have some element into the queue, and that we have already added a root. Then what we will do, we'll say queue dot will use poll, and we'll remove the root from the you can say queue, and we'll say this is our tree node, and this is nothing our current node, you can say. Okay, so we have taken a current node from there, from the you can say the queue, you can. Okay, now we'll check if the current node that we have taken is what, null, right? So what we'll do, we'll say if this is null, we'll update this one, not false, but we'll say now this should be true. Okay, now this will become true. If not, right, means else, then we'll go to here, and we'll check if this one is what we can say true. Let's suppose if this is, we have some value in here, if this is true, let's suppose, then it should return what, false. Okay, if not, let's suppose if not, then what we will do, we'll check queue dot will do offer, and we'll add current node, we have current node dot left, and then similarly we'll add current node dot right. Okay, this is our right. Okay, after this what we will do, we have completed this one. So once this is all visited, all the node will return true. So that's all we have, right? What we have to do, we are going with level by levels, right? So first we will check what the current tree root will check, the root node will check. If root node is what not null, right, then we'll continue this one, and we'll check if current, will check current node is null, then we'll check we'll make it root check is null, otherwise we'll continue this one. Okay, what I did, first of all we'll check if root is null, will return true, this is a complete binary. If not, then we'll add on to the queue, and from the queue we'll get this current node, and we'll check if it is null, we'll make check node is null, and we'll check the current node is true, then return false. Otherwise what we'll do, we'll continue this one. Left and right we will add on to the queue. All the levels we will add on to the queue. And so let's submit this one. It's working fine for me. Okay, so if we'll talk about the time complexity, right? So time complexity, what here TC will become what, O of n, because all the nodes we will traverse, right? We are traversing all the nodes. And if we'll talk about the space complexity, right? So we are storing all the value, all the nodes onto the queue, and that's why we'll say O of n. Okay, so that's all we have for today. Thank you so much, guys. Thank you so much for watching this video. If you like this video, please hit subscribe, so that I will get motivated to create the videos on the time. Thank you so much.